Hello everyone and welcome to another instructional video on analog to digital converters. So this is part of lab number 5. So in this video what we are going to do is we are going to learn how to use the analog to digital converter feature of the PIC16F877 microcontroller. So the PIC16F877 microcontroller has a built-in IDC feature which is able to convert analog inputs into digital values. So let's look at the aim. The aim of this lab is to learn how to use the IDC feature of the PIC microcontroller, um, interface analog circuits to the PIC 16F877 microcontroller. So we learn how to interface an analog input to the microcontroller, and then number 3, write programs to convert analog signals into digital signals. So we'll learn how to do that. So let's look at the schematics for this lab. So if you look at the schematics, it is given on page 2, which is figure 1. So in this schematics, what is included is a 16:2 LCD connected in a similar manner as in the last lab. So it is used in 4-bit mode where the data pins of the LCD D4 to D7 are connected to D4 to D7 of the microcontroller. The control pins connected in a similar manner where E is connected to E0, RW is connected to pin E2, and RS is connected to pin E1. And there is a potentiometer connected in this way where the terminal, one of the terminals, or the middle terminal of the potentiometer is connected to VEE. So this potentiometer is basically used to control the contrast, but it will not make a difference in the simulation. Now on the input side, so the LCD is an output. On the input side, we have a variable resistor connected to pin I0. So please note that all the pins that are marked as IN, like IN0, IN1, IN2, IN3, IN4, IN5, IN6, IN7. So there are 8 pins marked as IN from IN0 to IN7. So these pins can be used as analog inputs. So pin I0 is marked as IN0, which means this pin can be used as an analog input. Now, these pins can be used in both analog and digital mode. We have to set, by using functions in our program, we have to set or specify for these pins to be used as analog input. Now, I've connected a potentiometer, which is a variable resistor, to pin I0. So note that as I vary or as I turn the knob on the potentiometer, the voltage input to this pin is going to vary. So one of the terminals is connected to VDD and the other one is connected to ground. And so as I turn the knob from one side to the other side, what you're going to see on the analog input pin is voltage going from 0 volts, which is ground, to VDD, which is 5 volts. So that's what you're going to see in the simulation. Now moving on to the source code part. So source code, this source code is given in your handout, and this is exactly what I have created in my PIC-C compiler. So as you can see here, so first line hash include 16F877 standard. Now the second line here is hash devices or hash device IDC is equal to 8, and it says restricts IDC port to 8 bits. Now the PIC microcontroller IDC can be used in either an 8-bit mode or 10-bit mode. So what this means is an analog value will be converted to a digital value, and it will be stored as a 8-bit integer or 8-bit number. So that's what it means. And if you change this to 10, which is also what PIC16F877 is capable of, up to 10 bits IDC. So if we change this to 10, the analog voltage will be converted to a digital value, which will be stored as a 10-bit digital value or 10-bit integer. And the second and the third and the fourth lines standard from the previous handouts. Delay, we are going to use 20 megahertz, and we are going to set these configuration bits. Fifth line, stdlib.h. So we are going to use one of the functions from this library. Again, line 7 to line 13, we are defining which pins of the microcontroller we are going to interface the LCD pins to. So pin E0 is defined as LCD enable pin. So the microcontroller pin E0 will be connected to LCD enable pin. Pin E1 is defined as LCD RS pin, and so on for the rest of the pins. So you can change these pins to any pin on the or any digital pin on the PIC16F877 microcontroller. Next, we are including LCD.c. So this is the driver for LCD, which provides functions such as LCD_INIT and LCD_PUTC. So for us to be able to use those functions to display something on the LCD. Now void main, in the void main, what I have is int I. So int I is basically just a variable which we'll use in our for loop, and then unsigned int value. Now the reason why you have an unsigned in front of int is because a default int will be able to represent both negative and positive values as an 8-bit. So by default in a PIC program, an integer is an 8-bit integer. So if you put unsigned in front of int, it means that you are limiting the value that is to be stored in this variable to only positive integers. Unsigned means not signed. That means this value is not negative. It's only positive values. So positive values, and if you have an 8-bit storage capacity for int, so you can represent values or decimal values from 0 to 255 that can be stored in this variable value. And then there's another variable called value char, and it is an array. So it is a character array capable of storing 20 characters. So this is a character array. Now the next three functions, these three functions configure the analog to digital converter module on the PIC16F877. So these are high-level C functions that are provided with the CCS C compiler. And if you want to know what these functions do, what we can do is simply go to the help file. So if you click on this help button on the right hand side, if you click on this help button and click on contents, so it will come to this, and if you go to functional overview, one of the topics here is functional overview, and if you click on IDC, now over here you can see a description of all the functions that we are using in our program here. So we can see a description of all the functions. So for example, we are using setup_idc, and we're using this string here. So basically what that means, if you look at this function description, it says, and if you click on this is the link. So it says the function of that function is configures the analog to digital converter. It's available on devices with built-in analog to digital converter. It requires constants are defined in the devices.h. So we have 16f877.h file included. So what this function does, it accepts an input as mode. So mode is analog to digital mode. and the valid options vary depending on the device. So some of these options are IDC off, that means we are not using analog to digital conversion feature. IDC clock interval, so basically this means that we are going to use IDC and an internal clock for the IDC conversion. And there are other options as well. So we're using IDC clock internal. So this is our option that we are going to use. Now the next function, setup underscore IDC underscore ports. So if I go back and if I click on the second function here, setup IDC ports, you can see that the function of this is sets up the IDC pins to be analog, digital, or a combination, and the voltage reference to use when computing the IDC value. So the value or the input that you provide is also defined in PIC16F877.h file. So if you look at under examples, so one of the strings that has been used is all underscore nlog. So if you want all the pins to be nlog, that is what I have shown you in the schematic, pins which are labeled AN0 to AN7. If you want to make all those pins analog inputs, then you use this option. But in our case, we are using this RA0, RA1, RA3 analog. So what this means is that we are going to use pins I0, I1 and I3 as analog, and the rest will be digital. So rest of the AN pins will be digital, apart from I0, I1 and I3. And the voltage reference that will be used is 5 volts. So voltage reference is basically, it says reference is an optional constant specifying IDC reference to use. It says by default, the reference voltages are VSS and VDD. That means any value between VSS and VDD that you provide through the ports, through the analog pins, can be converted into a digital value. So if you supply a voltage outside that reference, the converter won't be able to convert that or represent that as a digital value. So, and then there are other options which you can see and read through this help file. The next function that is given in my program is set underscore IDC underscore channel, and we're using 0. So this function set underscore IDC underscore channel, it says it specifies the channel to use for the next read underscore IDC call. So read underscore IDC is the function that will retain a digital value, which is an integer value corresponding to the analog value that is seen on the port. So before using this function read underscore IDC, we must specify which channel we want to read from, because we can have multiple channels configured as analog inputs like I0, I1, I2, I3, and so on. So IN0 to IN7, so these are the channels. So if you select the channel as 0, that means IN0, the pin corresponding to IN0 will be used to read the analog input. So channel here is the channel number to select, and the channel number starts from 0 and are labeled in the datasheet IN0, IN1, and so on, which I showed you in the schematic. So in our case, we are using channel IN0. So we have to specify 0 here. So when we set the channel, we are ready to read from this particular pin. So, and then if I go back here, there are other functions that you can read about. So for example, read IDC, it says this function will read the digital value from the analog to digital converter. And you can have it in this way, where you say value is equals to read IDC. Normally we don't pass anything into this function by default in our program. So what it will do is read from channel 0, in our case channel 0, and it will store the value that it reads as a digital value in the variable that it returns the value to. And you can see examples given here as well, code examples. So this is how you can use the help file in for any function in CCS C compiler. So you can go to the topic, especially go to functional overview. So whatever peripheral you are looking at, you can go to that peripheral and you can look at the associated functions that you can use for that particular peripheral. So let me close this. Now, the next function on line number 28 is LCD underscore INIT, and this function is going to initialize the LCD. Then there's a while true loop, while one. So this loop is going to loop continuously. LCD underscore put C. So this function clears the LCD, and then value is equals to read ADC. So this function is going to retain a digital equivalent of the analog value, analog voltage value read at channel AN0, which is pin I0. And then the next function sprintf. So sprintf function is from the library stdlib.h. So what it does is you can specify a string, or you can convert a number or an integer or a float into a string. So that's what this function is. So this function in this case accepts three inputs. The first input is a character array, which is this, in which it will store the string equivalent of let's say a particular value in integer or float or in other types. So the string that it is going to store is given here. So this is the string it's going to store. So it will store I/d value is equal to, and then this %u. This %u means unsigned integer. So this will be replaced with the value of the variable value. So value is an unsigned integer. So whatever the value of this variable is, it will be replaced here in this string. So this is like a printf format character, %u, which you might already know from C++. So id value is equal to, and whatever the value of this value is, which is being read from the ADC, it will be put here or replaced. It will replace %u, and then this whole string will be stored in this value underscore char, which is an array of 20 characters. So it can only store a maximum of 20 characters, 20 characters or less. Now each line of LCD is capable of displaying 16 characters because we have a 16:2 LCD. So we iterate through from I is equal to 0 to I less than 16. So it is going to, this for loop is going to run 16 times, and it is going to display all these characters on the LCD, because these characters and this integer value is converted into a character and stored in this variable value char. So since this is a char array, we are going to display character by character on the LCD. So we have to use a for loop to do that, to display character by character on the LCD. And then after that, there's a delay of 1 second, and then it repeats again, clears the LCD and repeats again. So what this means is that at every 1 second interval, my analog to digital converter or my program is going to read a digital value corresponding to an analog voltage value on pin I0, and it is going to display the digital value, so the digital equivalent. So since this is an unsigned int, the digital value will range from 0 to 255. And please note that since my reference is VDD, that means 0 to 5 volts can only be represented within this range from 0 to a digital value from 0 to 255. And basically that's what this program is going to do. So if you compile this program, if I go to compile, rebuild, no errors, so it compiles successfully. And now if I go on to my simulation, I go into my Protus program. So this is the schematic that I have created, which is exactly the same as in the lab handout. So if I right click on my PIC16F877 device, I can go to edit properties. I have to change the processor clock frequency to 20 megahertz because in my program I'm using clock 20 megahertz, and then the program file. So I'm going to specify the lab5.hex file, which has been generated after I compile my lab5.c file. When I compile and there are no errors, a lab5.hex file is generated, which is here, and then I can click open, and that program will be linked to this microcontroller. Then I can click on OK. Now I can move on to run the simulation. So if I run the simulation, so you can see that it displays an ID value of 255. So my voltage here, using the potentiometer, I can vary the voltage that I'm supplying to pin A0, which is analog channel 0, AM0. So when I use the potentiometer, I can, so currently the voltage input, as you can see here, is 4.995, which is 5 volts. So I can change it, make it less. And as I keep on changing it, you can see that my AD value changes. My AD value here on the LCD changes. So as I decrease the voltage, analog voltage, my digital value representing this analog voltage decreases as well. And so since I can only provide 0 to 5 volts, I can make it go all the way to 0, let's say, and you can see the value changing on the LCD. And if I go down to 0 volts, all the way to 0 volts, you can see that ID value is 0. That means for a voltage input, analog voltage input of 0, my digital value is 0, which is an 8-bit 0. And as I increase, my digital value changes. And the maximum value, digital value is 255, because that's all the memory that we're using to store the digital value, that is 8-bit. So as I move to 5 volts, as I increase to 5 volts, my digital value changes to 255. So this is what the simulation is going to show. Now, if I go to the handout, so now in this lab, a potentiometer is interfaced to pin A0. Notice the correct way of interfacing the potentiometer. Pin A0 can be used to provide analog input signal. A port can be adjusted to provide a voltage signal between 0 to 5 volts, as we have seen in the simulation. And a 16x2 character LCD is interfaced to PIC16F877. Now the second note is on the source code, which I have already explained, which is why we use the hash device IDC is equal to I directive. How to use this function: set up IDC ports, and set IDC channel. And then there's a function read IDC to read the IDC. And then the last function is sprintf and what it does. So this notes also explains what I have already explained in this video. Now moving on to the exercise component, it says try out the following. Carry out an experiment by providing an analog voltage signal on pin A0 from 0 in steps of 0.5 volts up to 5 volts. At each of these analog values, note down the digital value displayed on the LCD. Tabulate your results. Come up with an equation that converts the digital integer value back into voltage value. You have to take into consideration certain things such as the range of the input signal and the resolution of the ADC. So the resolution of the ADC is 8 bits. That means it can represent unsigned integers from 0 to 255. Now use this equation in the program above to display on the LCD the analog value or analog voltage on pin A0. Note that you will have to slightly modify the program. So what I'm going to do is I'm going to tell you how you can do this exercise, or I'm going to do this exercise for you. So let me switch over to the whiteboard. Okay, so we know that the digital value changes as we increase or decrease the analog input in our simulation. So what happens is, let's say if we try to graph whatever results we get, it will be like this. So my handwriting is not very good. So let's say you have V on the y-axis, and let's say you have on the x-axis digital value. So we know that digital value goes from 0 to 255. So let's say this is 0, and our voltage goes from 0 to 5 volts. So as we increase our analog voltage from 0 to 5 volts, our digital value increases from 0 to 255. That is if we are using 8-bit ADC. So if we change the bits to 10, then this value would be a different value. Now, so basically it is a linear relationship. So if I try to plot this relationship, it will be like this. So it will intersect here. So it will have a linear relationship from here to here. So what we are trying to do is find the equation of this line. So we are trying to find equation of this line so that in terms of V and digital value, so that we can use this in our program to display the voltage value that is detected on pin A0. So the equation is similar, so you can use the relationship y is equals to mx plus c. So y is equals to mx plus c. C is the y-intercept, which is 0. M is basically the gradient of this slope or of this line. So the gradient is change in y over change in x. So change in y is 5 minus 0, and change in x is 255 minus 0. So basically we can say y is equals to change in y is 5 minus 5 minus 0 divided by 255 minus 0 times x plus my c value is the y-intercept, which is basically 0. So what we have is y is equals to 5 over 255 times x. In other words, my y is V. So my analog voltage is 5 over 255 and my x is digital value. 5 over 255 times digital value. So this is my equation. So now what we can do is program this equation in my C program and see if it is able to display the voltage value that is detected at pin A0. So the changes that you have to make in the program are as follows. So first, you have to declare a variable as volts because this is what we are going to calculate, and the type of this variable is float because it will also store floating point values or decimal point values. The next change is after reading the digital value, which is this value, we have to convert this digital value into analog value, and the equation that we got was 5 over 255 times the digital value. So volts is equals to 5 over 255 times value. Now I'm using 5.0 and 255.0 so that a floating point division can be done here instead of an integer division. And I'm using this float to ensure that this whole quantity, this whole calculation is done in floats, and the result is a float, which means a decimal point value. So you have to insert the equation. So this is the equation that we have inserted in our program. Next, we have modified the sprintf function. So instead of putting id value is equal to, we are putting volts is equal to %3.2f. So this is another printf format, %3.2f. So you can search for printf formats online or in this documentation. So what this means is we are going to display a floating point value here, and the total number of values will be 3, and there will be a decimal point after. After the decimal point, you'll have 2 values. So that's what this means. And then over here, I'm putting, instead of value, I'm putting volts. So that it should display volts now. Volts is equal to whatever volts is detected on pin A0. So now let's go on to my simulation and let's start to run the simulation. So schematic will remain unchanged, but when I run the simulation, it will use the new program to run the simulation. And you can see now it displays volts and whatever volts it detects. So in this case, it detects 2.9999, so it displays volts as 3 volts. And if I change here, you can see the volts changes. If I go all the way up to 5 volts, should display 5 volts. So, and then if I come down to 0 volts, uh, 2.79, 2.74, 2.49, 1.5855, go all the way down to 0, and it displays 0 volts. So now what we have done is modified the program to display the voltage that is detected on pin or the analog voltage that is detected on pin I0. Now, for those of you who are doing a project which involves using analog sensors like temperature sensor or whatever type of analog sensor, please note that your sensor is going to give an analog voltage value which you'll read using pin IN0 to IN7, whichever you decide to read to use. So you can, using this lab, you can now convert the, you can now display the voltage that is detected. But please note that sensor data sheets, they have equations of converting the voltage output to the sensed quantity. So for example, if you are sensing temperature, and let's say for voltage of 0.8 volts, the temperature is 80 degrees Celsius, then you can convert these volts appropriately using equations in your C program to temperature, and you can display temperature instead of volts. If you are detecting pressure or any other quantity, then the sensor data sheet will have a relationship between the voltage output and the sensed quantity that it is measuring. So you can use that relationship, put it in the program, and display the appropriate uh, sensed physical quantity. So with that, that's the end of this instructional video. Thank you.